Consider any positive integer n. If a and b are any integers congruent to modulo of n, that is denoted as then n divides a minus b. If a and b are congruent to n, then n divides a minus b. For example, if 3 and 24 are congruent to mod 7, then this implies that 7 divides 3 minus 24. 3 minus 24 is minus 21. We know that 7 divides 21. Let us solve a theorem about this. Theorem is that for arbitrary integer a and b, congruent to mod n, if and only if a and b leaves same remainder on dividing them by n. They are given that for arbitrary integer a and b congruent to mod n, if and only if a and b leaves same remainder on dividing them by n. Proof. We know that if a and b are congruent to mod n, then n divides a minus b. N must divide a minus b. This implies that a minus b is equal to nk. If n divides a minus b, then we can express it as a minus b is equal to nk. Now, rearranging this equation, a is equal to, shifting b to right side, b plus nk, we get b plus nk. Then consider if we divide b by n, then b leaves a remainder r such that b is equal to nq plus r. If we divide b by n, then it gives us nq plus r by rules of algorithm. Now applying this value into this, then we get a is equal to, in the place of b, nq plus r plus nk. This implies a is equal to, here n is same, n q plus k plus r. So b is equal to nq plus r when we dividing b by n. Here a is equal to nq plus k plus r. This shows that both a and b leaves same remainder r when we divide a and b by n. So this is the conclusion, that a and b leaves same remainder when we divide it by n. Now conversely assume that a and b leaves same remainder when we divide it from n. Then consider a is equal to n q1 plus r, b is equal to n q2 plus r. Then a minus b is equal to n q1 plus r minus n q2 minus r. a minus b is equal to, r minus r becomes 0, nq1 minus nq2. a minus b is equal to n into q1 minus q2. This shows that n divides a minus b. Hence the proof.